Hello. I would like to welcome everybody to the workshop 10 of Vehicular Technology Conference of Fall 2023. This workshop is Smart Spectrum Sharing and In-Band Coexistence for Non-Terrestrial Networks. And my name is Karabulut-Kurt. I am an associate professor at Polytechnique, Montreal. I'm also an adjunct research professor at Carleton University. And today my talk's title is Secure and Reliable Communications for Satellite Mega Constellations. Before starting my talk, I would like to thank the organizers and in particular to Professor Svadesti for this kind invitation. I hope you like the content. So the outline of my talk has several stages. I'll first start with the description of space network source, the 6th generation. So we are looking into more than transparent satellites. We are looking at networks, smart networks that are on space, not necessarily for Earth, but for also space exploration. Then I'll go back to the concepts of security with a focus on physical layer security. Then I'll talk about the wireless cyber physical systems, what they imply and how they are related with these space networks. And then I'll connect it to by looking into the security in wireless cyber physical systems. I'll talk about physical layer security tools and give an example of a jamming case, and propose a preliminary security framework for wireless cyber physical systems. And before concluding, I'll give a future outlook on the possible cross-layer security solutions. Now, the space networks towards 6th generation. So 6th generation is pretty much mature with the International Telecommunication Union recommendations. But for a long time, it is features have been discussed. We are looking into very ambitious transmission criteria with 1 terabit per second data rates, perhaps, and then support of mobility of very, very high speeds, like 1,000 kilometers per hour. And we are hoping to use additional components in these networks, like the use of metasurfaces, and more on the optical wireless communication systems, the use of terahertz communications with the high frequency bands. So we have selected some enablers to achieve these ambitious goals. My main focus on this transition is basically the space networking component. The space networks, currently we already have satellite networks from private companies. The current picture that we have is on the left side. So you can see that there's a standalone satellite network through a mega constellation, and with new constellation plans getting more concrete every day, like Amazon's Project Kuiper. So we have a standalone space networks with some a few connections with the terrestrial counterpart. On the terrestrial side, we have the 5th generation deployments in congested urban centers. We can even use UAVs as base stations to help with the traffic management. But they are two separate entities from one another. What we would expect to see in the full deployment scenarios of the 6th generation is the integration of the satellites with the terrestrial networks from an intelligent perspective. In between, we may make use of UAVs as conventionally taught. Also, we can also make use of high altitude platform stations like stratospheric devices to connect the satellite networks with the terrestrial networks. The overall network will become rather complex to manage, and for that we can, of course, resort to artificial intelligence-based solutions for network management and control. So this is the transition we are expecting. And if we are, if you look at, if we make it, if we look closely to these components, we have on the top layer, we have a LEO network. This may also be supported with other layered satellites like a GEO over the LEO. So the low Earth orbit satellites are located, they could be located from even 250 kilometers up until 1200 kilometers from the surface of the Earth. They move very fast. So they cross continental North America about 7 minutes. So we are looking at a very fast moving top network. And then we are envisioning a relatively stationary stratospheric network that can manage those LEOs and also help with the communication aspects. And we will not only serve the classical sense, we will not only serve the rugged terrains that are not suitable for ground deployments like polar regions. We are also looking at congested urban areas. So this is a vertical network, and whenever there is a mobility component associated with the network element, I always tend to think of them as a robot. So we are looking at flying robots, basically, even for satellites with predefined trajectories. They still can change their location and position based on the transmitted ground signals. So this is a vertical network and composed of mobile networking elements. And what do we expect to see for the in the near future? Till we are looking at a non-terrestrial network. Maybe I should come back to here and this picture and relate it with our workshop. Now, for the non-terrestrial network component, we may also have UAVs, and anything that is not Earth-bounded is considered as an element of the NTN, non-terrestrial network. So the LEO constellations, the HAPs constellations, perhaps, and the UAV clusters, they're all components of the non-terrestrial networks. Of course, what we should see to make sure that these NTNs are viable from a business perspective, so that they don't go bankrupt. We are looking at a close collaboration and cooperation between non-terrestrial networks and the terrestrial networks. And we have all these elements: LEO satellites, high-altitude platform stations, and the drone swarms. And we are not only looking at those elements for connectivity purposes towards Earth, but we are also looking at very ambitious lunar missions, as you may be following from the news. So these, say, space components from our Earth-bounded networks will also be useful to cover and provide services for lunar exploration and deep space exploration. So the security aspects of these networks are not very frequently thought of, and I would like to bring that into our attention. We are looking at cyber-physical components, both aerial and space network side, and their security will be more challenging, because now, if you are considering a terrestrial network security, we set up a base station and leave it there. But now this is no longer true for the use of high-altitude platform stations, for example. So the security will be for sure more challenging, and it is more than the communication information. Communication and location must be protected. And there are, of course, a number of attacks that can be considered from that perspective, both the passive attacks and the active attacks. And we also need to understand new threats. So it's not our conventional attacker that we are trying to find solutions against. The attackers also get smarter as the networks get smarter. So we should look at these security aspects more closely. So what kind of new threats are we talking about? This is a simple example. There can be just looking at one connection between a ground station and a satellite. The telemetry telecommand TT&C signals are sent over the air. So with a smart attacker, only targeting a specific portion of the frame, we can actually cause significant. This kind of an attacker can cause significant damage to the network. Just a false command to the satellite may disrupt the whole orbital dynamics. So we need to understand these new threats and their possible consequences, and then come up with, of course, solutions, good countermeasures against those. So I'll come back to this picture, but this is what I'm envisioning for the in the near, maybe not so distant future. Now we have this air network, but they are more than the communication components. They will do multiple functionalities, including computing, like edge computing, including caching for fast content distribution, and also control. And any kind, like any kind of link in this kind of a picture is wireless. So they are prone to some attacks, including jamming and spoofing. And we are also looking at cognitive connected autonomous systems that will be that will help us serve efficiently while we are exploring extraterrestrial bodies like a moon in this case. So going back to the agenda, what are the basic physical components of the security in this kind of setup? If you look at the security from a OSI reference layer perspective, we have the physical layer, from physical layer up to application layer. So we are looking at the open system interconnect reference design. Security doesn't exist. So how do we address the security solution? Security doesn't exist in the OSI layer, and it also comes with a number of requirements, including the secrecy, authentication, data integrity awareness, and robustness. So these are all rather challenging requirements. So starting with the secrecy, we need to make sure that the information is only obtainable by the legitimate receiver or receivers. For the authentication, we need to be able to identify and verify the user's identity. We should make sure that the data is not compromised. Its integrity is kept. So this introduces a requirement for the trustworthiness of information over its entire life cycle. And finally, we want robustness against denial of service attacks, or any kind of jamming or natural performance degrading effects such as solar flares. Should be combated, and we need to make sure that the system works in a reliable manner. So that robustness is rather important for the communication scenario. And going back to the classical security literature, we have different kinds of attacks. We have active attacks, we have passive attacks. The active attacks are the attacks where the attacker can generate a signal and transmit it. And the passive attacks are where the attacker is silently listening. So the active attacks are more, let's say, rather relatively easier to detect. The passive attacks are more difficult to detect because the attacker doesn't actually emit any signals. And in this case, if we are looking at even in the traffic analysis, the attack can be rather dangerous. So for a very simple traffic analysis attack exploits the Bluetooth traffic pattern of a home, and then the thieves have I read that from a newspaper article. Apparently, the thieves detected the lack of activity at home and then broke into the home, just looking into the Bluetooth traffic. So we cannot do much against the passive attacks. That is a issue. And the most well-known, of course, the passive attack is eavesdropping, where the eavesdropper captures the information in an illegitimate manner. But there can be also traffic analysis attacks, which are much simpler to do. While even if the data is encrypted, traffic analysis attack can be performed. So other issues, the classical solutions for active attacks are also rather computationally expensive, and they require some additional support, like the key distribution, and the issue that the fact that we are looking at space-bound networks interfering to the network is not that simple. Additionally, we would like to have low computation solutions. We would like to have limited battery. As we have limited battery, we would like to have energy efficient solutions. This makes the security problem a bit more difficult. So we don't have a space setup, but we are trying to do some imagine what kind of attacks can be let's say designed, and how can we find solutions for that. And one type of attack that we wanted to, let's say, explore is from the perspective of joint communication and localization. In the literature, the attackers are somehow they are not evolving. I don't know why. The networks are evolving, they are getting smarter, but we are still looking at like a rather simple, say, attackers in the physical layer. Now, in this work, we try to understand how can we detect if the attack pattern is time varying, and if it's coupled with the transmission of the legitimate users. And we try to implement it in a software-defined radio setup. And this is the attacker node, and we have a number of legitimate nodes defined. We tried jamming and spoofing in this kind of a scenario. And it is possible to detect them, but we need to understand more about the pattern of the attacker. So that is basically our main observation from those experiments. I'll come back to that. So the issue about all these things is the wireless channel. Wireless channel has a broadcast nature, and it has random fluctuations. So if we see a fluctuation, we don't know if it's natural or intentionally introduced to the channel. And also we cannot detect the presence of an eavesdropper. It's merely just consuming the signal that is captured by its antenna. And this is a very classical model, like the path laws and the propagation models are rather complicated in the presence of multiple trajectories, so in terms of multi-path fading. And we don't know what to expect even in the normal case. And we come up with some designs for this, for the path laws, for large-scale fading, small-scale fading. We come up with different distributions, and we try to understand what is normal and what is not normal. So if I come back to the OSI reference model, the security is basically, it doesn't exist, but we need to address it in all layers. So it's not only a specific layer we are looking at, we need to address it at all layers. So physical layer security, conventionally taught as a, let's say, separate add-on component. It needs to be, let's say, assessed as a natural extension of the rest of the security procedures with the regular encryption techniques. So I'll come back to the definition of the cyber-physical system. I claim that the satellites and the high-altitude platform stations and drones are cyber-physical systems. So these are basically the formal definition by NIST includes the combination of the cyber world and the physical world to obtain a cyber physical system. And it's mostly targets different industries. And here we are with the non-terrestrial network perspective. We are looking at aerospace industry. And the main components extend much beyond communications. We are talking about ubiquitous sensing and the actuators like the propellers in the satellite. We are looking at control systems and embedded computing. And we are looking at a diverse set of scales, starting with the planetary scale, going down to the nanoscale for biomedical applications. So in wireless cyber physical system, we are looking for each CPS application. We have different operational requirements. We have different challenges, and the security and quality of service are mostly evaluated separately, whereas separate goals may come up with contradictory design criteria. For example, if we want to eliminate the presence of eavesdroppers, we can reduce the signal level. If we reduce the signal level, quality of service may degrade because we are reducing the signal to noise ratio. So we are looking at a complex interaction between the users and the devices. And if you want to look at their security, we are looking at a multidimensional performance description. We have the operational goals, we have the security goals. Security goals are like a rather conventional CIA triad: confidentiality, integrity, and availability. But the operational goals are they change for each application that can target the stability, that can target the application specific functions, the energy constraints, additional resource constraints like the timing and the bandwidth, and also we need to support heterogeneous platforms. So this is from in our earlier work with Özgün. So we envision each application as a different kind of, let's say, entity. In these kinds of in this exam analogy, we used flowers, and for each application, we have different requirements, different challenges, and different implementation criteria. So we need to custom fit this to the aerospace industry and the MTNs as well. And regarding the common attacks and countermeasures, as you can see from the picture, we don't have a one solution fits all, checks all boxes kind of perspective, unfortunately. So we need to make sure that we have a number of tools to be able to address these attacks. So what are we looking at? We are looking at a distributed control system that is composed of the actuators, the physical system, the sensors, and the network. And each connection can be wireless. Wherever there's a wireless communication, it generates a vulnerability. And if the attacker is smarter, it can exploit more than one of them. And we need to come up with solutions for these kind of scenarios. So overall, the only solution to be able to detect an outside attack for each wireless link is basically looking into what goes on in the physical layer. So physical layer entity, I like this picture of Özge. We need to make sure that the data is preserved at every possible layer, including the physical layer, and we need to understand. We need to make use of the physical layer information to detect the presence of an attacker. So what are the tools that we can use? We can use, of course, frequently there are eavesdropping countermeasures like artificial noise and beamforming. They are frequently, maybe not so frequently used, but the RF-based fingerprinting, like physical layer authentication techniques, and then there's a detection of smart jammers. In the beamforming, the classical eavesdropping countermeasures include beamforming. In the beamforming, we are basically trying to make sure that only the legitimate user can detect the signal. And we can combine these with other technologies like multiplex transmission to generate interference intentionally. This intentional interference is usually frequently referred to as artificial noise. If it's quantized, we call that artificial interference in our work. So these kind of basically solutions, of course, they may be good, but they are actually consuming more energy, and also haven't been proven. We have tried to prove them very simply with software-defined radio setups, and you can see that the eavesdropper's constellation can be distorted if we just turn on all the interference and the noise components. So it is it can work, but still we don't have applications that are outside the laboratories to demonstrate this. So for the authentication, there's also a large body of literature on the key extraction from the channel, and we have tried to do that. However, there are some concerns about the key refreshment rates and the key lengths and the key error rates. So for that, we tried to find a solution to combine a physical layer extracted key, like a channel-based key, with an embedded key, and we obtained actually promising results based on that. So we can get, for example, 180-bit or maybe 120-bit key with a acceptable error rates. Of course, then when we do that, we need to also make sure that we eliminate all the errors between the keys as well. So other types of solutions that we can use is, one of them is this jamming detection and identification scenario. We are basically we try to identify the requirements to detect the presence of a jammer and identify its characteristics. And the attacker, as I mentioned, we try to make it a bit more smart and understand the vulnerabilities of the wireless link, actually, on the impact of wireless link to the communication system at the end of the day. And here, the ML machine learning techniques come into our rescue. So we have the transmitter and the receiver, and the received data, we process it with in time frequency transformations and understand what is going on in the atmosphere. Oh my, not the atmosphere in this case, in the lab, of course, but that's the idea, to be able to understand what's going on in the constellations. And this is a simple test bed picture. We have the jammer, the transmitter, and the receiver. So if you look at the transform domain pictures, we can easily understand the presence of an attacker with different attack criteria. So we used neural networks to be able to detect those in the setup. Convolutional neural network, the CNN architecture is shown in this picture. And we can get good results with neural network-based solutions, both CNN and RNN techniques. So our observations is, for this kind of a solution, we need to make sure that we have a good training data. It must be accurately designed, of course. Then this needs some sort of a collaboration between the attacker. We don't know how to do it in practice. It requires a significant amount of data. Time varying conditions are a bit difficult to capture, and we also need to evolve and make sure that we have better algorithms at the end of the day, other than CNN and RNN. So we look at the overall picture that should be in satellites, of course. Now, for the security framework, we are looking at the perceived risks by a context manager. There can be an adaptation manager for the transmission policy selection, and then this selected policy should go to the configuration manager to manage the connections, but the communications between the sensors and the actuators. And these perceived risks can be against the presence of an eavesdropper or an active attacker like a jammer and spoofer. So we tried to do that kind of a scenario very simply in the lab and change the transmission characteristics. Of course, now in this kind of a setup, the quality of service restrictions come into the picture. For example, if we have low energy requirements, then we need to actually tune the parameters so that we don't consume a lot of energy, especially if we don't need to transmit at very high data rates. So we have been doing some work on this regard, and I would like to conclude with what we need to see for this vertical network from the security perspective. There are these architectural challenges coming in with the vertical architecture, and we are looking at high mobility nodes, of course, and not all of them are moving in the same direction. And we are looking at an extremely time varying like a scenario. Also, we are looking at the rather difficult, as in the scope of the workshop, rather difficult spectrum harmonization problem. We can use non-contiguous frequency bands, and we are looking at from microwave, millimeter wave up until terahertz, sub-terahertz perhaps. We can then include free space optical communications and visible light communications in the picture. So how will we make sure that they coexist together? This is a very interesting research problem that needs to be solved at this point. And then if I zoom out again, the same problem appears for the space networks. How will we address these issues? We are actually looking into that problem with our research group these days. One of the solutions that we are looking at is one of them is the device skill, cognitive skills. And so we need to make sure that each device is smarter, and then with those we can actually come up with better coexistence approaches between all these nodes that we cannot intervene manually. So to conclude, the satellite networks and non-terrestrial networks, they are cyber-physical systems. They have tight operational requirements than wireless networks. We are looking at more than communication. We need to localize them and manage them. So they have a more complex nature. The security aspects is even more critical, and we should have a better perspective to design these security aspects. So for that, I actually would like to inform you about, maybe you already know, there is a new standardization activity that has recently started, IEEE SA 3349. And in this setup, we are trying to understand the security threats and then come up with a secure by design approach for space communication systems. So if you are interested in that, you're more than welcome to join. So I would like to thank you for your attention. And if you have any questions, please email me from gunesh.kurt@polymtl.ca. And thanks again for the organizers for this excellent opportunity.